In the previous lecture, we learned the first method to find the Taylor expansion of a function, which is by direct computing. So we find the pattern of the first few derivatives to find the expression for the nth derivative. Then we substitute that to the formula of Taylor expansion. In this lecture, let's look at the second method, which is to use term-by-term differentiation or integration from the functions that we know their Taylor expansion. Let's look at the first example. Let's find the Maclaurin series for cosine of x. Note that for cosine of x, we could also use the first method, direct computation, just like in example 1 from the previous lecture. But you can also note that cosine is derivative of sine. So it will be easier if we could just differentiate term by term of the Taylor expansion of sine of x. Just a quick recap. From the previous lecture, in the first example, we found that sine of x equals the series x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial, then minus x to the power of 7 divided by 7 factorial, and so on. Then we can use the relationship between cosine and sine. That is, cosine of x equals to the derivative of sine of x. But we know that sine of x can be expanded by a power series, so this also equals to the derivative of its power series. That is the derivative of x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial, and so on. Then we can simply take the derivative of each term. So the first term, derivative of x is 1. The second term, the variable is x cubed. So we have 3 times x squared, then divided by 3 factorial. Then plus, derivative of x to the power of 5 is 5 times x to the power of 4. Then the constant is 1 over 5 factorial. Then minus 7 times x to the power of 6 divided by 7 factorial, and so on. Then note that the constant in front of x is the last term in the factorial in the denominator. For example, the second term, we have 3 factorial in the denominator, and 3 factorial is 1 times 2 times 3. So the last term, the 3, can cancel out with the 3 in the numerator. So we'll be left with 2 factorial. So this also equals 1 minus x squared divided by 2 factorial. The next term would be plus x to the power of 4 divided by 4 factorial. Because the 5 got cancelled out, then the next term would be minus x to the power of 6 divided by 6 factorial, and so on. And we can use what we learned from the theorem. The theorem says if a function f of x has a power series, then the derivative of the series or the integral of the series will have the same radius of convergence. And since we've proved that the Maclaurin series for sine of x converges for all x, so by the theorem, the differential series for cosine of x will also converge for all x. So here's the summary. We found that cosine of x can be expanded by a power series. It equals to 1 minus x squared divided by 2 factorial plus x to the power of 4 divided by 4 factorial, and so on. Or if we write that in a sigma notation, we get the sum for n starting from 0 of negative 1 to the power of n, then times x to the power of 2n divided by 2n factorial. And this series converges for all x. Now let's look at the second example. Here we want to find the Maclaurin series for the function x times cosine of x. Since we already found the Maclaurin series for cosine of x in example 1, then we can simply multiply the x to the series. X times cosine of x also equals to x times the Maclaurin series for cosine of x. That is the sum for n starting from 0 of negative 1 to the power of n, then times x to the power of 2n divided by 2n factorial, which also equals, I move the x to the numerator since they have the same base, so this also equals to the sum for n starting from 0 of negative 1 to the power of n, then times x to the power of 2n plus 1. The plus 1 comes from the x before the sigma notation, then divided by 2n factorial. Now let's look at the third example. Find the Maclaurin series for the function arctangent of x. From calculus 1, we know that the derivative of arctangent of x is 1 over 1 plus x squared. The derivative of the function f of x equals to 1 over 1 plus x squared. And we've already found the power series for function of this form, which is the geometric series. So let's rewrite this as 1 over 1 minus negative of x squared. Then I can replace x by negative x squared in the geometric series. So this equals 1 minus x squared plus x to the power of 4 minus x to the power of 6, and so on. But the Maclaurin series I want to find is for the function f of x. Then we can use the fundamental theorem of calculus. F of x would be the integral of f prime. So the integral of 1 over 1 plus, let me define another variable, t squared, integrated from 0 to x. Then I substitute the series I found for 1 over 1 plus t squared. So this equals to the integral from 0 to x of 1 minus t squared plus t to the power of 4 minus t to the power of 6, and so on. Then I can integrate term by term. The first term, integral of 1, that equals to t, so I have t minus second term, integral of t squared, that is t to the power of 3 divided by 3, then plus t to the power of 5 divided by 5, then minus t to the power of 7 divided by 7, and so on. And I'm integrated from 0 to x. So I substitute the upper bound and minus the lower bound. So I get x minus x to the power of 3 divided by 3 plus x to the power of 5 divided by 5 minus x to the power of 7 divided by 7, and so on. Or we can rewrite that in sigma notation. It equals to the sum for n starting from 0 of negative 1 to the power of n. And we notice that the exponent is always an odd number. So we have x to the power of 2n plus 1. Then divided by the same value of the exponent. So divided by 2n plus 1. And a quick note from this result. If you remember from the beginning of the section, in lecture 12, I gave you an example of a value could be expressed as a series. And we can actually prove that from this function. At x equals to 1, then arctangent at 1 equals to pi over 4. And if we substitute 1 into this series, we get 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, and so on. And that is the example I gave in lecture 12. I told you that we can express pi over 4 in this form, and now we are able to prove it using Maclaurin series. Let's look at one last example for this lecture. Let's approximate the inverse of the hyperbolic sine function, and we are going to approximate up to x to the power of 5. Just a quick note, the hyperbolic sine function is defined as this function here, e to the power of x minus e to the power of negative x and divided by 2. And we know that the derivative of this inverse function equals to 1 over square root of 1 plus x squared. And I can rewrite this as 1 plus x squared, then to the power of negative half. So the function, by the fundamental theorem of calculus, it equals to the integral of f prime. And let's define another variable t, integrated from 0 to x. So this equals the integral of 1 plus t squared to the power of negative half, integrated from 0 to x. And the integrand is a binomial function with k equals to negative half and x equals to t squared. So I substitute this to the binomial series. This equals integral from 0 to x of the binomial series 1 minus half times t squared, then plus 1 over 2 factorial times k, that is negative half, then times k minus 1, so negative 3 over 2, then times x squared, and the x here is t squared, so we have t to the power of 4. And since we are approximating the function up to x to the power of 5, and here we already have t to the power of 4, so after we integrate this term, we'll have a power series to the degree of 5, so we don't have to worry about the other terms. And this equals, we integrate term by term, integral of 1 equals to t, and we evaluate it from 0 to x, so that is x. Then the second term we have half times t squared. Integral of this, we get t to the power of 3 divided by 3, and the constant remains the same. So we get negative of x cubed divided by 2 times 3. Then the next term, I have the constant 1 over 2 factorial, then times 1 over 2 and 3 over 2. And the integral of t to the power of 4, we get x to the power of 5 divided by 5 after substituting the bounds. And here we already have a degree of 5, so we don't need to worry about the other terms. So this is an approximation of the function up to degree of 5. And that is the end of the second method. We differentiate or integrate term by term of the power series. Let's take some break in the next lecture and let's do a summary of all the power series we've learned so far. Then the lecture after the summary will look at the last method, which is using combinations of power series.